Welcome to Deep Learning. Today we will study the problem of learning of sequences. Sequences really are everywhere in our world. They are speech, for example, actions in videos. Examples of application could be video summarization or music recognition. But they're also forecasting, for example, the weather, markets, the politics, and so forth. So if you think about what we studied so far, we have been working on a convolutional neural network of the type that is feed-forward. So these are usually like a combinatorial circuit. They take inputs, that are static inputs in time, and they give you an output. And if you give the same input in time, they keep giving you exactly the same output. In reality, in our world, it doesn't always work like this. Like in circuits that you need the combinatorial circuit to do operation, but you also need sequential circuit to remember what happened in time. Similarly, we need the new kind of machine learning algorithm or neural network that is able to learn sequences. Obviously, even a normal neural network could remember sequences because at the input, you could give them a sequence of steps, and so the static inputs are used as step number in time -10, -9, -8, and so forth up to the present, right? But this would be ineffective because you are fixing the sequence, and most of the time you don't know how long that sequence would be. So they're not really used for this kind of application unless you have a very short sequence that you need to remember. That might be, turning basically a sequential problem in a combinatorial one. But our world really is made of sequences. If you think about it, most of our learning is to move, and we move to see, and we move to augment, optimize our state. In order to do this, there's always a concept of time. There's only a concept of actors and actions. And we need to be able to predict what's going to happen. So similarly, we want neural network to be able to remember the past, to pay attention to important parts of the past. Because as you see in our everyday life, for example, there could be a long sequence that really has no importance, but there are just a couple of events that are important. So this we're going to study in this lecture and the following lecture as well. So if you think about learning sequences with neural network, for example, up to now, basically what we've done is the first one, one-to-one, the first one on the left. One-to-one is similar to the problem that we've investigated so far, categorization of images. So image to category, you input an image or you input some static data, and you want to know, what's in that data. Okay, that's a very interesting problem. There are other interesting problems that require learning sequences. And this could be a one-to-n kind of problem where, for example, you have an image, but you want to caption it. So now you want to create a sentence that you will be able to describe the image. So now you need to remember what you said in the past. So you need some kind of a language model. So now the input is really just one. But as you want to produce a sentence with all the components, then you really need to know what you said before. So you need to remember a sequence and create a sequence. There's also the number 3, example number 3, many to many. This could be, for example, language translation, but also could be action recognition. So language translation, for example, you want to hear a whole sentence or a big chunk of it, and before you can start translating it, right? So you'll have a sequence as the input, and then you have to remember what has been said, so you have to keep it in a state, and then you have to output the right translation. The last one could be end-to-end, so at every step, for example, you have an input, and at every step you want to give an output. And that could be if you want to summarize a video, or if you want to describe a movie to somebody who's watching it, and most of the times you'll have an output. So these are some kind of learning sequences, and we'll discuss more examples in class as well. So the tool to do this, and what we're going to look at today, is a recurrent neural network. So a recurrent neural network is a special kind of neural network that is designed to remember sequences. So in its simplest form, this is a recurrent neural network. Is a network that remembers as a state, remembers its past. So you think of this neural network as the X is the input and H could be the state / output, right? We somehow need to feed back the memory of a previous steps. So we're gonna need our neural network A, the green box, to remember the previous state. So how do we do this? See, really, a recurrent neural network can be unrolled in time and look a lot like a regular neural network, if you think about it. So what you see on the left with the feedback could be unrolled in time into what you see on the right, and now you see that the inputs basically at each step are have a timestamp, so timestamp 0, timestamp 1, timestamp 2, and so forth, up to the last one, right? And then what we propagate from one green module of neural network to another is the state, and then we may or may not produce output at every single step. Okay, this sounds really all great, and definitely, has been investigated for decades. One of the big problem that was only solved not exactly recently, but I would say, but in '97, so many years ago, is the problem of long-term dependencies. So this is the problem where, let's say you are trying to describe a story, right? Mary went to the kitchen, John went to the kitchen, Mary and John are cooking breakfast, John went to the bathroom, and now you have a question, where is Mary, right? Now you have to go back way in the past to remember that Mary went to the kitchen. Okay, so you need to save that kind of information in the state for a long time. Now this is a simple example, but when you read the novels, big, large novels, you have to remember many pages in the history. So there are two concepts here that come into play. One is you need to remember your history, and second, you need to pay attention to the story and remember only the important portion. Okay, forget the second part for now. We will discuss it later in class. And it's really part of active research. What we want to do today instead is we want to really focus on learning the sequences. So if I'm trying to produce a sentence, the moon is shining very bright tonight. In order to produce shining and bright, I need to know what I'm talking about. I need to know about the moon. So I need to remember what I said before. That is the problem. That is the state. In order to remember what I said before, I need to have a machinery that allows me to do that. Now, I highly recommend you to read this paper about LSTM. We'll give you some more insight. But basically, the problem of LSTM is the following. So if you try to remember, if you want to output H3, and now you need to go back in memory and remember X0 and X1, because H3 really is, for example, in my sentence, the moon is shining bright tonight. If I want to say bright, I'll need to remember that I refer to the moon, so which is one of the first inputs. But now, if you look at the gradients, so when you train this network with backpropagation, you have to remember that basically you have to adjust the weight based on the input. Now this input has been going through several steps of several time steps, and the weights, which may all be less than 1, are multiplied by many times by other weights, just as like in this formula here in the middle. If you want to compute the gradient, of the last of these neurons, and consider this as one of the neurons in the diagram above, they are multiplied by W2, W3, W4, and so forth, right? So 3 weights. If they're all less than 1, and they're all multiplied by other weight less than 1, then we get a problem, because, for example, if you have weights that are 0.1 and 0.1, 0.1 4 times, then their product becomes really tiny, right? They're becoming smaller and smaller in each time step. So as you try to remember things in the past, like 10 time steps before, you find yourself not able, because the number became too small, and it's difficult with the precision of the machine to remember this. Remember, in our brain, in a low precision machine, we might have even less number of bits. We have only 8 bits or 5 bits or so forth. So this is really a problem we need to solve. So this problem limits RNN to just a few iterations in time. And it was not enough to solve interesting problem, at least until the LSTM, new techniques like the LSTM were invented. Okay, so how do we solve this problem then? We use a long short-term memory module that comes from the paper that I just listed before. The long short-term memory module is the one depicted here. Don't worry about it. We'll explain now step by step. Just to look exactly at what we mean by each element. So, for example, we'll still have the input X. H will now be the output. As you can see, it looks like an output. And there could be another state, which is the arrow on the top going horizontally. Look that the yellow boxes are neural network layers, linear layers with their own non-linearity. So sigma is the sigmoid, and tan H is the hyperbolic tangent. And we have pointwise operations like plus or multiplication or tan H. And then when we split, we say we copy, and when we combine, we say we are concatenating 2 values. Okay, so let's go through the LSTM, long short-term memory module, one step at a time. So long short-term memory module. First of all, let's look at the top horizontal bar. So that basically describe the state, right? So now the state, instead of propagating through directly from one neuron to the next, and having this problem of vanishing gradient, instead is basically gated by other inputs. So as we go through, let's see the first gating, for example. So what happens here? Actually, so the input and the output have their own function. There's a neural network layer here where WF is the neural network matrix, the matrix of this layer. Sigma is the sigmoid. So what we're trying to do here is we are combining the features of the previous output, HT minus 1, with the current input, and we're trying to figure out which part of these are important for the state. Okay, so this is the first equation of the long short-term memory module. Let's move now to the second. So that this is interesting as well. So again, we have IT is basically a gating signal now that depends on the same input, the previous output h of t minus 1 and the input x of t. Now you see they're multiplied by matrix W of I, and again passed through a sigmoid. At the same time, we need to also process. So this is going to be our gating signal, I of t, right? At the same time, so this is I of t is actually the information at time t that we want to store or not, right? At the same time, c of t is basically the same two inputs. They are combined together with matrix the WC. And notice that now we use hyperbolic tangent here to basically process these inputs. So what is C of t? So C of t is basically a temporary state. So it's a state, C tilde of t is a temporary state that depends of the input and the previous output. Okay, so this is really, we want to process this input and previous input, current input and previous output. We want to process them with the neural network layer WC, right? At the same time, we are going to be gating this signal. So we want to decide, is this important at this time step to remember the previous output or the previous input, or only the previous output, or only the previous input? Because remember, WC could set all the weight for x to 0 and only remember the previous state, or could set all the weights for ht minus 1 to 0 and then only take care of the input and no need to remember the previous output. So all of this is possible, really. And then so what we do is that the state is actually the previous state multiplied by f of t. So the f of t is like a gating, right, mechanism, and as well as the state that comes from the current timestamp c tilde of t is multiplied by another by I of t, which is gating it. So it's deciding whether should we now add the new state to the old state, should we remember the old state at all or not? So if f of t is 0, we are only remembering new things from this instant, right? And likewise, if I of t is 0, we are only remembering the past, because maybe this time step has nothing. In a sentence, if I say the moon is very bright tonight, when I said and made a pause, that's really not important, so I should not remember it. So the network could decide to neglect that. So this is basically the really great intuition about LSTM, is the fact that we can gate the input, the previous state, and the output, decide what is important in each time step. Sometimes we want to produce an output, sometimes we want to remember the past, sometimes we want to really pay attention to the input. And so this is what this gating is doing. There's one more that we need to figure out, which is the output gating. So h of t. H of t, which is what we consider the current state, is basically the output O of t multiplied by the tan h. Okay, while instead OT is the output gate, and it's a sigmoid that multiplies the input again and the previous state through a weight matrix, linear layer, or a single layer of a multi-layer perceptron, single layer neural network with weights WO, right? Notice that if I go back 1 second, okay, notice that every time we have a gating, we use a sigmoid. And the sigmoid goes from 0 to 1 and basically decides, okay, should I remember things? Then it's 1, or should I forget things? Then it's a 0. Instead, all the neural network layer, there are two actually here. One is C tilde of t, go with an age, so they can swing from negative values or positive values, -1 to 1. And then so you see another gating here with the sigmoid. So this is basically the whole idea about LSTM. If you look at the whole equation that we showed you, they describe the LSTM fairly well. And again, the big really contribution of LSTM is let's not create the chains of weights through time. Let's put some gating elements there. So backpropagation and the data will decide when to remember something, when to remember the state, and when to output something. So this is really the key ingredient of this. Lastly, I want to show you the gated recurrent unit, also known as GRU. So this is just a slight simplification of LSTM that became popular recently because less equations mean less work for a machine to compute. So it's sometimes it's faster to compute this function. So if you see this gated recurrent unit is basically fusing the state with the output. We have a state and it corresponds to the output, and internally creates these internal signals. So it has, for example, R of t, that is the gating of the input, and then it has z of t, again, that is gating of the previous gating of the previous state as well. And then it creates h tilde of t, which is the candidate new state / output, right, with the neural network layer, and so forth. So this is a slightly simplified version of recurrent neural network, and it's very popular today.